Hey, welcome to the podcast. I've got Dr. Anya Sharma here. She's a computer science professor who literally wrote the book on internet protocols.
Thanks for having me.
So I was reading about this stuff, and ARPANET keeps coming up everywhere. Like, what was the actual starting point here?
Oh man, ARPANET is like the classic origin story. So ARPA conceived this thing in the late 1960s to link research sites together. Started with just 4 nodes: UCLA, Stanford, MIT, and University of Utah.
Wait, only 4? That was it?
Yeah, exactly. It was all research focused back then. They just wanted machines in different buildings to share files and processes, not like, Netflix traffic or anything.
Right. And protocols. I keep hearing about TCP/IP. Can you explain what a protocol even means in plain terms?
Think of protocols like agreed rules for machines. Who starts talking, who replies, how to check for errors. It's basically language and etiquette for computers. TCP, UDP, IP, HTTP, each one handles a different slice of behavior.
Okay, but I keep getting tripped up on TCP versus UDP. Like, they're both transport layer, but why would you pick one over the other?
So use TCP when you need reliability. Emails, file transfers, web pages. TCP does all the heavy lifting. Connection setup, sequencing, acknowledgements, retransmissions, congestion control. But UDP, use that when low latency beats perfect delivery.
Like what?
Games, live video, DNS queries.
Wait, DNS uses UDP? I thought DNS was super critical. Why UDP for something that important?
Good catch. DNS typically uses UDP because the queries are small and speed matters. But here's the thing, if a reply gets too big, DNS will actually fall back to TCP.
Ah, so it's like small, quick lookups over UDP, but big transfers can switch to TCP.
Exactly. And speaking of DNS, the whole structure is pretty cool. Root servers, top-level domains, authoritative name servers.
Hold up, root servers. Are those the famous 13 roots I've heard about?
Yeah, conceptually 13 named root server addresses, A through M. Although many are actually spread across hundreds of physical machines worldwide, they delegate to top-level domains like .com, .org, country codes.
So when I type google.com, my machine checks its cache first, then asks my ISP, then maybe the root.
Exactly that path. Local cache, then your resolver, usually your ISP, then root, then TLD, then authoritative server, then boom, IP address.
And then my browser connects to that IP with HTTP.
Right. And here's what's cool. Kim Berners-Lee built the World Wide Web to link documents. He created URLs, HTTP, HTML. The first website was at info.cern.ch.
So the web sits on top of the internet.
Exactly. HTTP's application layer using TCP underneath. Your browser makes HTTP requests, get, post, whatever. Server responds with status codes like 202, 404, 500.
You mentioned TCP handshake earlier. Can you explain the three-way handshake like I'm 5?
Sure. Client sends SYN with a random sequence number. Server replies SYN ACK, that's its own sequence plus an acknowledgement. Client sends ACK back. Now both sides agree on sequence numbers and boom, connection established.
Random sequence numbers, that's for security, right?
Yeah, exactly. Randomizing sequence numbers prevents easy spoofing of connections, and once you're connected, TCP uses all these sequence numbers, acknowledgements, checksums, retransmission timers.
I mean, this is wild. We've covered ARPANET, DNS roots, HTTP, TCP versus UDP, three-way handshakes.
Yeah, we went pretty deep.
Next time, we should actually look at packet level stuff like IP headers, ARP flows, maybe use some tools like DIG and TP dump to see this stuff in action.
Oh man, that would be awesome. Actually seeing the packets flying around.
Okay, so I was reading about this, and can we start with the transport layer protocols, TCP and UDP, right?
Yeah, exactly. That's where things get handed off to applications. TCP and UDP are like the main players here.
Wait, hold on. UDP first? I heard UDP is like connectionless and kind of reckless. Is that fair?
Fair and totally accurate. UDP stands for User Datagram Protocol. And yeah, it's connectionless. Basically just fire and forget.
So no handshake, no guarantees. That sounds dangerous for like emails and PDFs, right?
Exactly. You wouldn't use UDP for email or file transfer because packets can get lost, arrive out of order, or just get corrupted.
But it does have some protection though, right? Like checksums?
Yeah, UDP includes a checksum in the header to detect corruption, but it won't retransmit. It just says, hey, this is broken.
So the checksums detect, but don't fix. Got it. What's in a UDP header? Short version, please.
4 fields: source port, destination port, length, and checksum. Each port and length field is 2 bytes, so total header is 8 bytes.
8 bytes, wow. And payload size?
I remember some 65K number.
Right. Total datagram length is 16 bits, so payload max is about 65,527 bytes per UDP datagram.
And that's why DNS, gaming, real-time voice stuff use UDP, speed over reliability?
Exactly. DNS, voice calls, video calls, games, they'd rather drop some packets than wait for retransmits.
I showed me that TCP dump thing earlier, TCP dump -C5 to grab 5 packets. Seeing UDP packets like that was wild.
Love that tool. Great for seeing what's actually on the wire. Okay, ready for the other hero? TCP.
Oh yes, TCP is Transmission Control Protocol, and it's the reliable one, but how does it actually guarantee delivery?
TCP is connection-oriented. It does segmentation, sequence numbers, acknowledgements, retransmission timers, flow control, and congestion control, all working together.
Can you slow down? Three-way handshake first. I keep hearing that in interviews.
Sure, client sends SYN with a random sequence number, server replies SYN ACK, client replies ACK. Connection established.
Confused. Random sequence numbers. Why random? Isn't just counting up enough?
Good question. Randomness prevents easy spoofing. If sequence numbers were predictable, an attacker could inject packets and hijack connections.
Oh, wow, security baked right in. Then, during data transfers, sequence and ACK numbers keep everything in order and detect duplicates.
Confirming, exactly. Sequence numbers identify bytes, ACKs confirm receipt, retransmission timers handle lost segments.
And TCP is full duplex. Both sides can send simultaneously, but each connection is strictly between 2 endpoints?
Right. A TCP connection connects exactly 2 endpoints. You can have many simultaneous connections, but each socket pair is unique.
Ports and sockets. Quick refresher. IP picks the host, port picks the application, socket ties process to transport.
Perfect. IP equals device address, port equals application endpoint, socket equals the OS binding process to transport.
Last thing, HTTP uses TCP, so web browsing is reliable. DNS often uses UDP for speed. Email uses TCP. Anything I'm missing?
That's the core mapping. Just remember, transport sits above IP and below applications, and those trade-offs of speed versus reliability guide which protocol you pick.
Okay, so I was reading about this, and can we talk about framing and how bits actually become packets on a wire?
Oh, yeah. Framing is like this beautiful little ritual. The data link layer wraps network packets into frames, adds headers and trailers, then hands them to the physical layer to become actual signals.
Wait, so when you say,
Sorry, had a brain freeze there. What I meant was the link layer creates frames with source and destination MAC addresses, plus a trailer for error detection, usually a CRC.
CRC, so that's how it catches errors before bits get interpreted as higher layer packets?
Nodding, exactly. Frame-level error detection catches corrupt frames. If the CRC doesn't match, boom, frame gets dropped or retransmitted depending on the protocol.
Okay, and then the physical layer turns these frames into, what, electrical voltages, light pulses, radio waves?
Yep, all of those. The physical layer is literally the electronics and media. Copper voltages for Ethernet, laser pulses for fiber, RF for Wi-Fi. It's the lowest level conversion of bits to signals.
So framing is more than just packaging. It's how devices agree on start and stop, byte boundaries, error checks.
Right, there's framing for sync with preambles, addressing with MACs, control bits, and trailers for error detection. It's like the link's contract.
You mentioned MACs, so every interface has a MAC. My phone's Wi-Fi and Bluetooth have different MACs?
Yes, exactly. MAC addresses are per network interface, so Wi-Fi, Bluetooth, Ethernet, each can have its own 12-hex digit MAC.
Okay, so when two devices on the same LAN communicate, they use MACs, not IPs.
On the local link, yeah, they use MACs. The IP layer deals with logical addresses and routing between networks, but the data link uses MACs to actually deliver frames on a physical segment.
And ARP fits here? How does a host learn another device's MAC for a given IP?
That's ARP, Address Resolution Protocol. A host broadcasts an ARP request asking,
Wait, you cut off. What does it ask exactly?
right, sorry. Device A wants to reach 192.168.1.4, so it broadcasts, hey, who has 192.168.1.4? Tell me your MAC.
Got it. So, putting aside our little ARP dance, let's jump up one layer. IP addressing, IPv4 versus IPv6. Give me the short facts.
IPv4 is 32 bits, about 4.3 billion addresses. IPv6 is 128 bits, around 3.4 times 10 to the 38th addresses.